AP Physics, UT Quest, assignment Gravitation and Planetary Motion. This one particular problem on your assignment, it's a total energy of a satellite at altitude, and then it's total energy of the satellite at impact, and then it says how much energy is lost due to air friction. Okay, we're going to take this one piece at a time. This is your given information, and here you're given information. There's a few key things that you need to pay attention to. First of all, your altitude is given in kilometers. That must be converted. Your impact velocity is in kilometers per second. That must be converted to meters per second. Okay, and then we have this statement right here. Let the gravitational potential energy at 0 be at r equal infinity. Well, what does that mean? Well, that was our hippie physics definition for potential energy. Remember, we let potential energy equal 0 way out in deep space because we don't have a gravitational force there. So there's our expression for potential energy, and this is what we're going to need in this problem. And now it's really just kind of an energy conservation problem. Okay, let's start here with this satellite at some altitude h here. And we did this derivation in class. So here I'm orbiting, so I have a tangential speed. This tangential speed is defined by speed of a satellite. I have this potential energy from my potential energy equation with 0 at infinity. And we put it all together. I mean, you could work this equation like this, and it's really kind of a mess. But in class, we put all this together, and when we did it and simplified and all this other kind of stuff, we came up with this overall equation for total energy of a satellite. And this is a combination of kinetic energy and potential energy. Okay, so the first thing we want to do here is we want to calculate this total energy at altitude. Okay, right now we're just at a plug and chug. Just make a particular note of what you're doing right here, what I'm using for R, okay? So it's the radius of the planet, Earth this case, plus altitude. What does that do? That gives me this total distance center to center. And that's critical in all the work that we're doing in this particular section. Okay, now once we have that hammered out, okay, that's one of your answers. Now let's look at the total energy at impact, and we have to look a little bit different. All right, so my energy total at impact, I've got kinetic and potential energy, and let's break these down and see where we're going to handle it. Now here, the kinetic energy is just going to be my traditional 1/2 mass of satellite velocity squared. This time my velocity is not a tangential velocity, it's an impact velocity, which is given in the problem. All right, so again, here we can plug and chug and be a little bit careful. What am I using here for distance in my potential energy equation? Okay, I have now at the surface of the Earth, I've dropped potential energy, so this should be a larger negative value than it was before. All right, so that's my total energy at impact, and you enter that in the second part of the problem. Okay, now if you were to do a complete energy conservation on this problem right here, it would impact with a much higher speed than what was actually given. And the reason it impacted at a slower speed is because of air friction. And this actually comes a pretty easy computation. All I do is just I take the energy of the first two parts and I just subtract them. So my energy at altitude is different from my energy at impact, and the reason they're different is because I lost some of that energy due to the work done by air friction. And that then answers the last part of that problem on, let's see, this guy right here. Energy lost due to air friction. And that wraps that problem up. Good luck.